In this video, we'll discuss the energy source for the sun and some older hypotheses about what could be producing energy for the sun. Just some background questions, food for thought. What would happen on Earth? How would our lives be different if the sun right now went dark, if it stopped sending energy to the Earth? Would it have an impact on us? Well, certainly. At night it's colder than during the day. So imagine 12 hours of night, another 12 hours of night, another 12 hours of night, another 12 hours of night. It would not be long until the Earth was frozen solid, on the outside at least. There's some energy source inside the Earth, radioactive decay, but we would be in big trouble on the surface. We have to go live underground. So how many more years can we rely on the sun to give us energy at about the rate that it is doing so today? What's the lifetime of the sun? So those are some important scientific questions. And let's see what we can discuss about them. In the 1800s, this was a question about where the sun's energy came from. And we have the Industrial Revolution coming on, and some hypotheses that were put forward would be perhaps the sun is on fire. It looks hot. You put your hand up and facing the sun on a summer day and your hand gets warmer. Fires are hot. You put your hand in front of a fire, your hand gets warmer. So one idea was that the sun is on fire. It's burning. There's combustion. The problem with this is that the sun's lifetime in the past is extremely long. It's already been around over 4.5 billion years. Scientifically very confident that our solar system is older than 4.5 billion years. So we have to have a fuel source that'll last 4.5 billion years. The calculations show if we have combustion as the source of energy, the sun would have a lifetime of just a few thousand years. Whatever wood and oxygen would be there to supply the combustion, given that the mass of the sun was all wood and oxygen, or coal and oxygen, or oil and oxygen, you name it, whatever's burning doesn't really matter. But the lifetime would just be a few thousand years. So that's not long enough. We've had recorded history that's longer than a few thousand years. So we're not relying on combustion for the energy source. So a later hypothesis was that there were impacts of asteroids and comets on the sun. Those impacts would warm up the surface of the sun as they came in. They're carrying kinetic energy that would warm up the sun. However, it would do some other things. It would also increase the mass of the sun for the amount of impacts to generate the energy that we observe leaving the sun. The amount of impacts would increase the mass significantly of the sun, and the orbits of the planets would change. We've not noticed a change in the orbits of the planets. And doing solar eclipse measurements into the past gives us some information on the stability of the size of the sun, apparent size of the sun in the sky, which tells us the Earth is a certain distance away from the sun. So there's no evidence that impacts are responsible for giving us energy radiated off of the sun. The mass is too big. It has to be added to the sun continuously to accomplish this. What about the sun itself just contracting, not changing its mass, but the outer layers just pulling in? Could that supply the sun's energy requirement? And it turns out here again, the lifetime for this is too short. If the sun is contracting inward, and in the early life of a star, that is an important feature, the gravitational contraction energy. But as far as being on the main sequence, a stable star, the Hertzsprung-Russell diagram being on the main sequence, that gravitational contraction can't supply billions of years of energy. It can only supply tens of millions of years of energy. So lifetime would be too short for a star that's supplying energy by gravitational contraction. And we've measured the diameter of the sun for over 100 years, and it's a very difficult measurement, but there's no evidence that the sun is changing size. So we don't trust the gravitational contraction theory. Well, what else could cause energy? Well, we know we have nuclear power plants where uranium fissions, and in that process there's less mass after the fission. There's energy produced by this fission process. So could nuclear energy be involved? Well, yeah, it might be. However, we can measure composition on the sun in the solar atmosphere, and there's some uranium there, but there's not enough to supply this energy demand that the sun has. There is another type of nuclear energy, fusion. In fusion, the process, the proton attracts, or not attract, the one proton approaches another proton. If they get close enough, they can fuse. So fusion, this has been used to make hydrogen bombs, unfortunately. It's being researched in a laboratory and there is fusion of hydrogen occurring in laboratories, but it hasn't been engineered and scaled up to a place where we can build a commercial power plant with the fusion process. That's a hope for the future. But in this process, roughly 4 protons become 2 protons and 2 neutrons. There's some nuclear physics that goes on here that we're not going to go into, but roughly we have these 4 protons merging and forming a helium nucleus, 2 protons and 2 neutrons. As this occurs, and there are multiple steps that I'm not going to go into, but as this occurs, the overall effect is that there's less mass in the helium than the 4 original protons. The fuel becomes helium, the hydrogen becomes helium, but the mass is not constant. There's a loss of mass. Some mass disappears, and this mass that disappears is energy. It's energy by, you can do the calculation with E equals mc squared, and take the energy radiated by the sun and divide by speed of light squared, and you can come up with the mass that's being converted to energy. So this is a viable mechanism. There is enough hydrogen fuel to allow the sun to shine at its current luminosity, its energy rate, for tens of billions of years. Not tens of, but 10 billion years, which is, in a human lifetime, that's a long time either way you say it. So 10 billion years would be the lifetime of the sun in terms of its basic fuel use. There'll be other videos coming in this series that talk about some of the changes that happen as a star's age. It doesn't just wink out and stop producing energy one day. There's structural changes that occur that are very interesting. Here we are, just saying why the sun produces energy. The hypothesis that's accepted has been shown to work in a laboratory of hydrogen becoming helium and releasing energy, is this fusion process. Hydrogen becoming helium, along the way some mass disappears, is converted to energy, and light comes off of the star. So let's talk more about this fusion. Let's just start at the basic. One proton approaching another proton. What would keep them apart? Well, they're both positive charges, and like charges repel. So it's not easy for this fusion to happen. If you have hydrogen gas in a car's fuel tank that runs on hydrogen fuel, you're not going to have a nuclear action occur. The atoms repel each other. They don't get close enough for a fusion to take place. It turns out there's a special mechanism that causes the 2 protons to merge together. So we've got this problem of like charges repelling. We can get the 2 charges close together. We can get the 2 protons close together if they're moving at high speed. If they're moving at high speed, they'll slow down as they get close together, but then they get close enough and fusion occurs. The 2 protons become a single object. So we have to have high speeds. The way we get high speeds is to have high temperature. Objects that have higher temperatures, the material is moving around at higher speed. Temperature is related to kinetic energy of a system, and that kinetic energy is related to the speed. I'm not going to go into the calculation, but like charges repel, We have to get the protons moving to high speed to get close. High speed requires high temperature. So when they're close enough, and don't need to know what it is exactly, but it's small, much smaller than an atom to be close enough, there's a force of the universe called the strong nuclear force. It's called the strong nuclear force because it works on the scale of the nucleus. That's where it's active. This force is active when objects are no further apart than the size of the nucleus. And it's stronger than the electrical force. So it's called strong nuclear force. We have less mass after fusion. Energy is released. I'm going to take a little pause here. So we have protons fusing together, hydrogen forming helium, and the numbers are a little bit striking. They're astronomical type numbers. But inside the sun, in the core of the sun, where we have enough density to get collisions to occur regularly, and we have enough temperature for the speeds to make those collisions give the protons a close approach to other protons, about 4 billion kilograms of mass disappears every second, becomes light. So it's not strictly disappearing, it's still in the universe, but now in the form of light, form of energy. 4 billion kilograms change to light every second. So 4 times 10 to the 9th kilograms. But the sun is massive. The sun's mass is 2 times 10 to the 30th kilograms. 2 times 10 to the 30th kilograms. So taking a look at the ratio here, you can see that what's being used every second is not a significant number compared to the mass of the sun. And doing the calculation, the sun can roughly keep its energy output as is, about the current level, for about another 5 billion years. There are some structural changes as the core of the sun begins to be deficient in hydrogen. I'm not going to talk about that in this video, but roughly 5 billion years of this energy output is available. In the fusion process, the summary then, the 4 protons, and an atom that has 1 proton is a hydrogen atom. So the 4 protons, the 4 hydrogens fuse together, producing energy, producing 1 helium nucleus, and then an interesting particle here, the neutrino, is released during these fusion reactions. So tremendous amount of material every second has to be converted to energy to match the energy that's coming off the photosphere of the sun and radiated out into space as light. So 4 billion kilograms, but the sun is very massive. It has a huge supply of hydrogen. We've got another about 5 billion years to go before we'll see significant changes in the structure of the sun. Okay, we might ask yourself, well, hydrogen bombs in the 1950s, they were built to blow things up, to be destructive. If we have this fusion going on in the core of the sun, and much more than what goes on in a hydrogen bomb, why doesn't the sun just blow up? Why doesn't it get out of control? If this energy is being produced in the core of the sun, why doesn't it just get more and more energy and blow the sun apart? Well, there's a thermostat for the sun, a thermostat, and called hydrostatic equilibrium. A couple of long words, but the concept is easy. Hydrostatic equilibrium. So we're in kind of a fluid material. The gas can flow around. So it's hydrostatic. Static, we have a matching of 2 forces. We're in equilibrium, a matching of 2 forces. If you would imagine being towards the core of the sun, above you there's a tremendous mass of material in the mass of the sun, and gravity is pulling that material inward. So there's this inward force that creates some pressure from the outer layers of the material trying to move down towards the core. The pressure that matches this inward pressure is an outward pressure of the gas. Having high speed for the particles, these particles bounce off of each other at great speeds and create an outward pressure. The 2 pressures, or the 2 forces, match, and we have a stable sun. It's not collapsing. It's not blowing apart. So we have right now hydrostatic equilibrium in the sun. The outward force caused by the pressure of hot material in the core is balanced by the inward force of the weight of the material. So we have an outward force balancing an inward force, hydrostatic equilibrium. The gas pressure creates an outward force, just like you blow up a balloon. As you inject molecules into the balloon, you're creating higher pressure inside. The balloon has an elastic stretch to it that resists going bigger and bigger and bigger. So there's kind of a match, an equilibrium size for the balloon as you blow it up. So we have a situation of hydrostatic equilibrium. The outward force from the pressure created by high-speed gas particles matches the inward force, the weight of the outer layers of the sun. What happens if we start to get this runaway explosion occurring in the core? If the temperature of the core goes up, that's going to increase the pressure of the gas in the core, and that creates more outward force. That makes the core expand. Gas that expands cools off, and we get the rate of fusion dropping back down. So if the rate of fusion goes up too high, then we have increased internal pressure. That's increased force, lifting the outer layers, and lifting mostly the core actually, but expanding the core. The core cools off and the fusion goes back to its standard value, its rate. What if the core temperature goes too low? What's our thermostat response if the core temperature goes too low? Well, if the core has a lower temperature, it's going to have less pressure, and the outer layers win. They tend to press in the core. That's going to contract the core. Material that contracts, gas that contracts, heats up. So the temperature will go back up, and the rate of fusion will go back up to where it needs to be to give us our energy output. So hydrostatic equilibrium, there's a thermostat that controls the rate of fusion. The sun is not blowing up. The sun is not collapsing. It's stable in its current life cycle. There are later stages of a star where this hydrostatic equilibrium is lost, and either the outward force wins or the inward directed force wins, and we'll talk about those in other videos. So that's the fusion. Now, mention neutrinos coming out of the fusion reaction. These neutrinos are very interesting particles. They have very, very little mass. They have a little mass, but much less than an electron, almost zero mass. They travel nearly at the speed of light, not at the speed of light, because they have mass. They cannot travel at the speed of light, but they're very close to the speed of light. They have very little interaction with regular matter, with any matter. Very low probability that they're going to cause an interaction where they're captured. It's not zero, but it's very small. So in the 1960s, astronomers started to build experiments searching for neutrinos released from the fusion reaction of the sun. So they could detect those neutrinos. There's not much interaction, but there's enough to be detected. And they can do a calculation as to how well they're detected. And what they came up with as a conclusion is that there are only about 1/3 of the number of neutrinos that were expected. Well, does that mean that the sun was 2/3 off and not producing much energy? Remember, it takes the energy about 200,000 years to get from the core to the photosphere where it comes off as light. Did the sun go off about 100,000 years ago, 150,000 years ago, 199,000 years ago? And that light signature is about to reach the photosphere of less emission of light to the Earth? It turns out no. The physics of neutrinos were not fully understood in 1960. So in the 1990s and later, better neutrino telescopes were built, better ways of capturing neutrinos and measuring them. The physics was understood better, and it turns out there's not just one type of neutrino. There are a few types of neutrinos, and the detectors of the 1960s could not detect all the types of neutrinos that were en route from the sun to the Earth. And won't go any deeper than that, but the neutrinos that are detected now, the number that's detected, matches the predicted number for the energy output of the sun. So fusion is going on in the core of the sun. It's confirmed by measuring neutrinos that come from those reactions. The neutrinos move right through the body of the sun. Regular light takes 200,000 years to get out of the core of the sun. The neutrinos are not hindered at all with the density that we have for the sun. The neutrinos can get out there and come back to the Earth, a little over 8 minutes. The neutrinos are here that were just recently produced in fission in the core of the sun. So the neutrinos are a probe of the interior of the sun, the core of the sun. They tell us that the fusion reaction is going on okay at a rate that matches the light output, the energy output of the sun. So we're all right. You can relax. You don't have to go underground to live. We're going to have sunlight for years to come. So that's our situation with the energy source for the sun. Combustion, just burning, cannot supply the energy. Impacts, things falling into the sun, can't supply enough increase in temperature to match the energy that's given off. We don't see the orbits of the planets change. We don't see the evidence that the mass of the sun has changed. And we don't believe the sun is contracting at a rate that would supply the energy. Calculations say that that would not allow the sun to last 1 billion years. So we have a 5 billion year old sun. Fusion gives us an energy source that can supply the energy rate of the sun for 10 billion years. And fusion involves protons moving at high speed because the temperature is high. They collide, they get close enough together that the strong nuclear force makes them merge. The strong nuclear force is stronger than the electrical repelling force if the protons are close enough. So there's our little summary of fusion. Read, ask questions, and we'll see you in the next video.